In the world of AI-powered language models, predicting the next word is at the core of how these systems function. For tech and AI professionals, understanding this mechanism is fundamental to grasping modern natural language processing architectures. Imagine typing a sentence and having an AI auto-complete your thoughts. This process hinges not on magic, but a dense web of statistics, mathematics, and learned patterns. In this deep dive, we will unfold the layers from the foundational concepts to the perspicacious mechanics underneath today's leading AI engines. Language modeling basics. At its essence, next word prediction is a probability assignment. Given a sequence of words, the model estimates which word is most likely to follow. Early approaches used n-gram models, strings of n words, statistically mapped to the word most frequently following that sequence. These models are simple, limited by their scope, and fail when context spills over the window of n words. The step-up came with neural networks, enabling longer memory and nuanced handling of context. Neural networks and word embeddings. Neural network-based language models, such as LSTMs and GRUs, introduced context awareness by mapping words to dense numerical representations called embeddings. Word embeddings capture semantic relationships. For example, in vector space, king and queen are closer than king and banana. Neural nets process these vectors, learning which sequences tend to precede which words. The prediction emerges from statistical patterns in these embeddings, allowing nuanced word selection based on context. Transformer architecture revolution. The arrival of transformer models marked a quantum leap. Transformers rely on self-attention. Every word in a sequence can weigh the relevance of every other word, regardless of distance. This allows global context integration, crucial for capturing subtleties and disambiguating meanings. In practice, the input, the text so far, is embedded and passed through stacked layers of attention and feed-forward blocks. The model dynamically emphasizes relevant words and patterns, generating a context-rich vector. Tokenization, vocabulary, and context window. Before any prediction occurs, the engine breaks text into tokens, atomic units that can be words, parts of words, or characters. Modern models use subword tokenization to handle unknown words and maximize vocabulary efficiency. The context window, how many tokens the model considers, directly affects performance. Larger windows enable broader understanding but require more computational resources. When the user types, the model processes these tokens, encoding the sequence into context vectors. The real prediction process. The core engine tasks, given past tokens, calculate a probability distribution across the vocabulary, assigning a likelihood score to each possible next token. This is achieved through a softmax layer at the model's output, an array of scores turned into probabilities. The model can sample or select the highest probability token. In commercial applications, methods like top K or nucleus sampling introduce randomness, allowing creative or diverse continuations. Training the model prediction accuracy depends on training. These models ingest mountains of text data, books, articles, code, conversations, learning correlations and context. Training involves optimizing millions or billions of parameters to minimize the difference between predicted and actual next words on real data. Over epochs, the model refines its mappings, compressing the rules of language, style, domain nuance, humor, and logic into its weights. Gradient descent and backpropagation. To train a model, the engine uses gradient descent, calculating how wrong a prediction is, then adjusting parameters to reduce error on the next pass.